Okay, so we have our review for Q111, which is the impulse momentum theorem and also conservation of momentum. So we'll start here with the old way, which is a two-step process. So we make a 111, calculate its weight, and realize the normal force is equal. And then we have an FP that's given. It's 410, and we'll have some friction as well, FFK, which we'll need to calculate. So we start by just taking 111 times 9.8, and you come up with 1087.8. That means that the normal is also 1087.8, and then if you multiply that by the coefficient of friction, which is at the top here, 0.3, we end up with 326.34 for FFK. So we have unbalanced forces in the X. So we do an X summation. And I say 410 minus 326.34. So we say 410 minus our previous answer, and we get a net force of 83.66, and then that equals ma. So we divide by the mass, 111, and we get the acceleration. So acceleration equals 7.54 meters per second squared. Remember, that's not our final answer. What we're searching for is the final velocity. In class, I've been using v prime. V sub f also stands for final velocity. So we can plug that into magic physics formula number 1, which starts at rest, and the acceleration 0.754 times the time we pushed it for, 25 seconds. So take your previous answer times 25. That gives us 18.84 for V final. So that's how we do the old way. Came up, oh, don't forget your units. So then we can also do the new way here. Same kind of business. We're going to sum the impulses. First of all, realize that the forces are canceling in the y, so there'll be 0 net impulse in the y. I want to focus on the x. So I say 410 times 25. Remember that impulse equals force times time. So if I take 410, which was FP, times 25, I get an impulse of 10,250. And then I want to do the same thing for the friction. Friction was 326.34, and I multiply by the time, 25. I get a number of 8158.5. So then I just need to find the difference, 10,250 minus 8158.5. So sum impulses, impulse created by FP minus impulse created by FFK equals mv minus mv. Considering that it started at rest, all this kind of goes away. So I'll have 2091.5 equals 111 times V final. So divide by 111 and we get 18.8 again. Either way you do it, it works. V final equals 18.8. So that's the top one, impulse momentum theorem. Now let's take a look at the bottom one, which is the conservation of momentum equation. So we need to find the final velocities. Of course, plugging in the simulator would be easier. You want to think about how three things are conserved or equal. So the forces are equal, the momentum before equals the momentum after, and then finally the energy before is equal to the energy after. So we start by just writing out the conservation of momentum equation. So we'd have, let's see, what is this, big M? big M times big V naught plus little m times little v naught equals big M times big V prime plus little m times little v prime. So we end up with this equation right here. This is the beginning. Put in what we can, 112 times 20 plus 23 times 5. So we'll simplify this. 112 times 20 plus 23 times 5. So the total momentum before is 2355, which is an important number. Afterwards, we put in what we can. 112 times v prime plus 23 times little v prime. And so now we have to find a relationship between the velocities before and after. If we look up here, we see there's a difference of 15. So afterwards, there'll be a difference of 15. However, things will change. Here, this one was going fast, so afterwards this speed will go down and this speed will go up. Now, they won't just switch because they're different masses, but we can predict that 20 will be less and 5 will be more, and the difference will be 15. So if we want to say that mathematically, we would say big V naught minus little v naught equals the opposite afterwards. Now, this is a problem. You have to really look at who comes first here, who's going faster, who's going to catch who. And that dictates how you write this equation. This equation might be little v sometimes first. That may happen to you on the quiz, so be aware of that as a possible stumbling block for you. So like we said before, this is 15, and then we want to distribute that negative. That's little v, and then I want to add big V to the other side, so I get 15 plus big V prime equals little v prime. So this is our relationship, and I want to sub it in right here for little v. So I get 23 times 15 plus big V. So now we have like terms of big V, but don't forget it equals 2355. So let's distribute here. So 23 times 15 is 345. And we also get 23 big V prime. So now I have to combine my like terms of big V. 112 plus 23 is 135 big V. I want to subtract 345 from both sides. So 2355 minus 35 is 2320. So big V, just divide here, must equal 17.185. That's what I got for big V. So if that's what 1 equals, that's what big V equals. Something's tragic here. Something has gone wrong. Let's see if I can figure it out real quick, because this isn't good. Is this where it is? Maybe this is where it is. Let me just double check. 112 times 20 plus 23 times 5 is 2355. 2355 minus 345 is 2. This must be it. 2010. 2010 divided by 135 is 14.88. Yeah, that looks more reasonable. Alright, so we'll say big V prime equals 14.88. We'll see how this works. So I'll put this in here, and that is a decrease. That's why we make these predictions, to catch problems like this. And so that means little v is 15 more, so we put in 15, and we get 29.88. So that one went up, the other one went down. Boy, it went up a lot. And we can now check by seeing if it equals 2355. So the moment of truth here, 112 times 14.88 gives me this, plus 23 times 29.88 gives me 2353.8. That's pretty close. It's not exact, but it's good enough to know that, you know, minus a lot of rounding here, we would have gotten it right. So I'm going to go with that. Alright, stay hard.